Attendance sheet. Going around. What's next Wednesday night? The exam. Very good. Did you guys get an email from the TAs on review sessions yet? All right, I'll make sure we get that out tomorrow. My understanding is similar schedule to last time. So I think we'll have one Sunday, one Monday, one Tuesday. Keep your eyes peeled for an email. Also, I will send out an email directly, or maybe we'll have Angie, our assistant dean, do it, about the makeup procedure. Same thing, right? Can't just decide you're going to show up and do the makeup. Got to reply to the email ahead of time. Let us know what the conflict is. Get an okay from us that says you're okay to do a makeup. Otherwise, we expect to see you at the Wednesday night exam. Okay. Homework 10 is posted, okay, which is on the material that we are finishing up today. Okay, and of course, homework 9, beams, the last of the stuff that is due for the exam, right? Due on Friday. You'll be able to get that back from your TAs early next week. No MATLAB homework new this week because looking at the schedule, it looks like you've got the final MATLAB supplemental in lab next week. Okay, and so if that's true, there'll be no new MATLAB homework posted. And that'll be it. That also means that for MATLAB, the things that will be really fair game for the MATLAB final, we tend to do a subset of all the types of stuff you did in those MATLAB supplementals. And so you'll be ready to go to start prepping ahead of time for that. All right, we do the MATLAB final during the last week of classes during the regularly scheduled lab meetings. Okay, so that's when that will occur. And again, that piece is worth 5% of your grade. So if you haven't spent as much time on MATLAB as you should have, okay, you still get some time to turn it around and get ready for that part of your grade. Okay. So before we move forward, okay, with more applications of integrals, I want to kind of recap again the asphalt problem we looked at last time. Okay, and I think we kind of left class at the end with the idea that it's the punchline was that if I want that area, all right, I'll try and fit it over here in the corner. Okay, if I want that area, then essentially what I can do, if this is 50 and this is 50, and I'm trying to figure out the crosshatched region right here, then it becomes kind of clear at the end, I ought to be able to take a quarter circle and subtract it from the square. All right, so this was the quarter circle. Okay, and so if the radius is 50, right, then finally here, this would be the overall square. So the exact solution here is 50 times 50, right, which is 2,500. Minus the quarter circle, right, pi r squared, that was 625 pi, right? Somebody get me a decimal number for that. Say again? 536.5. So 536.5, if this was feet, this is square feet. Okay, and so to 4 significant digits, that's the exact answer. And so one thing to kind of drive home this point further, we started with looking at, say, 4 rectangles. All right, we're going to put 4 rectangles in here and see what happens. If you look on the course page here, Josh is always putting up great MATLAB kind of resources, but even as part of the lecture materials here, he has what he calls the integral approximation demo. Okay, and so what that is just a piece of code that he wrote. Okay, and I cut and pasted that text file into an M file here. And this is it. So the goal here is for you to actually see, as you start ramping up the rectangles, how much of that area you actually get. Okay, and this is actually a pretty neat demo. So the exact problem that we just looked at, here it goes. Okay, and so he is stacking up the rectangles, right? And as they stack up, he's plotting the answer. What is the answer as a function of the number of rectangles? Okay, and here's the actual value. We're at 46 rectangles, 50. This is the beauty of computers, guys. Okay, and so obviously we're hitting kind of an asymptotic kind of point here, right? I mean, this thing is going to flatten out over time. In fact, after 200 rectangles, the curve is getting pretty flat, and we're getting close. We're at 530.5. This is 536.5. So we're at like almost 99% of the way there. Okay, 98, 99%. And you can change that number to be whatever you want. All right, the picture, you know, kind of interesting. This picture looks like you've pretty much got the whole thing. You can see these little bits of places where you're missing it still. Okay, so 99% of it just, you know, the key is jamming it up in here. This thing goes all the way up to 50. Getting these small enough that you can get this top little piece of area. It takes an awful lot. If you go all the way out to 1,000 rectangles, I think you're still only at 3 digits. You can't get the 4th digit yet. Okay, so, but obviously, if I put an infinite number of rectangles in there, then I would get this exact number, 2,500 minus 625 pi, okay, which is an irrational number. It's got a, you know, infinite number of digits. Questions? So if I ask you then, what is an integral? What's going to be your answer? Area under a curve. Is that what all integrals are? What kind of an integral gives you an area under a curve? A definite integral, right? When I got limits on it, literally that's what it is. It's an area under a curve. Could be square feet if I'm plotting actual lengths, right? And the area is square feet. Could be anything else. Y-axis times the x-axis, that's the units, right? So we're going to see all kinds of applications of definite integrals in mechanics, statics. We're going to start that today. Okay, next week also finish that and do dynamics, and then after that we'll even be in electric circuits. Okay, so tons and tons of applications. Sometimes we're talking about physical areas. Most of the time we're not, but we're always interested in areas under graphs. It tells us a lot of useful stuff. Okay, so then if a definite integral is an area under a curve, right, then what the heck is a indefinite integral? Area between 2 points. What was that? The I is infinite. Anybody? Just recapping from last time, 2 kinds of integrals, right? When I do a definite integral, I get what? An area under a curve. Is that a number or a function? It's a number, right? When I do an indefinite integral, I get what? I get an antiderivative. I get a function, okay? I get a function that if I take its derivative, right, the slope of the tangent line at any point gives me the other function, okay? So that's what it is, right? An indefinite integral is an equation, right? And it is the antiderivative of, you know, the thing I took the integral of, okay? And that's it, right? So understand, when are you just doing differentiation backwards as a mathematical operation, like to solve an equation that's got derivatives and integrals in it, okay? Then you're doing indefinite integrals mostly, right? But when you're actually trying to figure out, I got something plotted, need an area under a curve, then you're doing a definite integral. We good? All right, so moving forward, how are we going to use this stuff in statics? Okay, and in fact, I have to actually finish up, I think, a bit of the material from the last set of notes, okay, where we had a transition from these areas under curves to the concept of work and energy. All right, so somebody that's had some physics before. Do you guys remember when you did work in physics? If you want to be an engineer, you got to get used to doing work, right? Absolutely. What does work mean in a physics context? Yeah, go ahead. Yeah, force times distance, right? Force times distance. And what's the unit of force times distance? Newton what? Newton meters. That's one. Does anybody know what a Newton meter is called? That's a joule. Okay, and what else? It's another unit. Force times distance. Newton meters would be like in the SI, right? What if I'm in the English? Foot pounds is one. Okay. So, yeah, I can take force multiplied by length. What physical quantity does that represent? Anybody? If you had some physics before. When did you do calculations to figure out work? Force times distance. What's a joule? Energy, okay, so that's the point, right? Force times distance is energy. So in engineering, we use the concept of work, for example, energy conservation, energy balances and dynamics, right? I got a student, I tell you about this guy, does crash reconstruction now. Did I tell you about this guy? Yeah, my former PhD student, on the side while he was doing his PhD, he had some collaborators, wrote a textbook in crash reconstruction. All right, this guy gets paid like $250 an hour to sit in court and explain, basically whether or not the person's at fault based on like the skid marks and the damage to the vehicle and this. The beauty of this is you reach that certain level of expertise, and the stuff that he uses in court, I swear like 2/3 of it is content we cover in this class. This class, $250 an hour. And then he gets gigs like, he lives like in Oklahoma. He gets gigs in Florida, and then he drives. All right, and he charges $250 an hour the entire time he sits in the car. So, anyways, just trying to get you guys to think about entrepreneurism, right? But so work and energy, I mean, conservation of energy, energy balance, really critical to all aspects of engineering. All right, so that being said, let's see if we can think about, why do we do an integral in order to compute work? Okay, and so this is the concept of work. Okay, and this is something from really statics and dynamics, but really most fundamentally, it's physics. Physics 2400, you guys will spend quite a bit of time on work and energy. ME, for example, 2120, that's dynamics. Okay, and when you want to do integrals for work is when you're worried about forces that are not necessarily constant. Okay, so let's say I have a variable force, okay, that is pushing a block. Okay, and so here's my block right here, right? And let's say this thing is, being pushed along the ground. Okay, and the idea is I'm going to move this thing along with an applied force, and I'll just call that force F, but it's a function of x, right? So I'm going to start x here, right? And I'm going to move this thing all the way over, say, to this point here, which is some distance away. Okay, and so we'll say right here is x is equal to d. Okay, and so what happens is, if I have a constant force, and I apply a constant force over that distance, then I can use the basic definition of work, which is force times distance, energy. But if the value of the force is not constant, might not be, could be driving a vehicle, right? And the force I'm using could be changing as I go, right? Because I'm changing the acceleration, right? Because I'm driving through mud or driving on smooth, whatever it is. Okay, then to go from point A to point B can take a different amount of energy, right? Depending upon what force you use to get there. Okay, and so in that case, the way you think about this is you think, well, I really need this force, and every little bit of distance that I move it, right here, dx, right at this one point, I've got that force times dx. But now, 1 point over, the force is different. So I've got a different F times dx. Right? And so if you want to figure out the total energy, you just got to add it up. All right? So if I've got an infinite number of different points here between, x equals 0 and x equals d, then apparently I've got to add up an infinite number of these forces times distances. All right? And so if I have to add up an infinite number of anything, right, when one of the quantities is infinitely small, then what I'm actually doing is what? I'm doing an integral, right? So I got to add these guys up. So, what we will say at this point is really by definition, the most general definition of work is this one. W is an integral. It is the sum of the force at any point along the path multiplied by the distance traveled. Okay, and that distance is dx in this case. And the integral sign means I've got force times dx, which is work at any given point, but I now need to add that up over the entire length, integral from 0 to the distance d. Okay, and if we are in the SI system, right, this is the work. okay, and we would be Newton meters in SI, okay, or if I'm in the English system, common measure would be like pounds times inches, sometimes pounds times foot. Anybody work with cars at all? Yeah, they use a dimension instead of pounds times foot, they use something called foot pounds. What does foot pounds measure? When would you hear somebody, you know, in an automotive talk about foot pounds? Torque. Okay, so then you're talking about output of engines, like actual engine torque. Okay, so same units, it's energy, right? So you can relate all of that to essentially the fuel you put in and the conversion of the energy from the engine, right? It is ultimately related to the torque coming out. All right, great. So let's do some examples. Okay, and what I want to illustrate here is work. It's what we call path dependent. Okay, and so the point is just going from one endpoint, you know, beginning to end doesn't mean the work's the same, right? This f of x changes every time. I can get a different answer for the same distance. So let's look at this. If d is equal to, we'll use a simple number, 1.0 meter. Okay, what I would like to do is find the work w if, we'll look at three different functions. Okay, number one, let's try a polynomial. All right, f of x, we'll go with 2x squared plus 3x plus 4. Okay, and that's going to be in newtons. Okay, and for part b, let's do a trig function. F of x is equal to 2 times the sine. It's going to be pi over 2 times x. And then we'll have plus 3 times the cosine, okay, of pi over 2 times x. Okay, that's also in newtons. And then we'll do one more, part c. Let's look at an exponential function. What if f of x, okay, is now 4 times e to the pi x? Okay, and again, that guy is newtons. All right, so three different functions that can get me from point A to point B, traveling exactly 1 meter, should not expect to get the same answer, right, for the three different equations. All right, so let's do these one at a time. And as you can probably tell, all right, this is also an exercise for us in calculating integrals. All right, we've got a lot of people in the class that haven't worked integrals before this course. So if that's you, all right, you should probably have the sheet out just as a reminder. And the kind of integrals we work in here, all of these cases, all right, they are the derivatives backwards for the same things that you're already responsible for on your derivative sheet. Okay, if this stuff is old hat to you, that's fine, but otherwise, if it's new, feel free to have the reference there out. All right, so part A. I'm going to plug in f of x, right, 2x squared plus 3x plus 4 into this guy right here. Okay, so the work, integral 0 to d of f of x dx. Okay, so in this case, I know the d. It's the integral now from 0 to 1. Okay, and the f of x, 2x squared plus 3x plus 4 times dx. So I got to work that integral. Okay, and so if I think about this, you know, do I see a complete polynomial like that on the sheet? No, right? Just like we didn't see it on the derivative sheet. But what I have is I have a sum of three different terms. Right? And of course, right at the bottom, just like we had for derivatives, if I have the sum of the functions and I integrate, then the answer is the sum of the integrals. Right? And so what it means is I can do this term by term, one term at a time. Okay? And so what I'd like to do is just say, hey, the work is the following. Let's put the answer inside the brackets here, one term at a time. And then we'll evaluate the limits there at the end. Questions about the plan before we move forward? All right, so help me out. If you haven't had integrals before this class, okay, want to make sure everybody's with me. Do I have a volunteer? We're going to do this term by term. Who wants to integrate the first term, 2x squared? Good. 4x. Walk me through it. What do I do with the 2?
You move into the negative power?
This constant 2 in front, not this 2, just to be clear. What do I do with the constant in front of the x squared? leave it alone, just like in a derivative, right? So the 2 stays there. So now I just need to look at the x squared. So keep going. So what do I do if I want the integral of x squared? Okay, so you got the sheet, right? Is it a special case of what's on the sheet here? I got a sine omega x, cosine omega x, e to the sx. I got x to the n, c times f of x, and then the sum of the two.
So, I guess it's x cubed over 3.
Yeah, right? So what he said was this is a case of x to the n, right, where the n is 2. So if I have x squared, it's x to the n plus 1. You add an exponent, and then you divide by what you just added. So this is going to be x cubed divided by 3. Okay? And the 2's out front. How do you know if you did this integral correctly? I can just take the derivative, right? This is the beauty of this. We just finished derivatives. So if you want to double check, take the derivative. The 2 stays out front. The 3 comes down. Cancels this 3, x to 1 less power, right? And what am I left with? 2x squared. Okay? So you can check as you go. Yes?
Now, on the sheet, it has a plus c on the outside as a constant.
So this is a good question, right? He said, so on the sheet, it's got plus c for the antiderivative, right? And it's because on the sheet, these are formulas for antiderivatives, which are indefinite integrals. Now, I can put a plus c with every one of these terms. But when I do the limit process, I will evaluate the whole thing at x equals 1, and I will subtract the whole thing at x equals 0. So all of those constants will get subtracted off again. Right? So when you do the definite integral, it is customary not to waste the ink, right? And realize that, hey, there is no plus c in a definite integral. Right? In an indefinite integral, if you don't have it, your answer is incomplete. Right? So you really have to think about that. And in fact, we'll see that next week. Right? What those plus c's really are in dynamics, in circuits problems that depend on time, those plus c's enable you to get the initial conditions in there. Right? So they enable you to think about what was happening at t equals 0. Okay? And so those things really matter. Okay? But here, with limits on it, I don't need the plus c.
Why wouldn't 2 be the constant, though?
Well, so the indefinite integral of this first term is this. Okay? The 2 is already associated with this. I have to add any constant because if I take the derivative of the whole thing, the constant goes away. Okay? So this 2 right here, it is a constant, but it goes with this term. The plus c is a separate term. Okay? But if I add a plus c to every term, right, and then I evaluate the bottom limit, I'm going to subtract all the c's that I just added. Okay? And so it's the evaluation process that says I don't need the c's. Okay? Good questions. Yes, Beck.
For exam purposes, does it matter if we do that, like notation, versus just the 2/3 x cubed?
You mean if you write it 2 times x cubed over 3 as opposed to 2/3 x cubed?
Yeah.
Is that what you're saying?
But can we write 2/3 x cubed?
Yeah, so you can write it like that, 2/3 x cubed, or like this. Those are identical statements.
So it's okay.
Absolutely. Okay. Other questions? Very good. All right, so first term. Then you move on. I got the second term, 3 times x. Who wants to take a crack?
3 halves x squared.
So it's 3. I integrate this. I get x squared over 2. Right? And so again, you could write it as 3 halves x squared. How about the last term? I got 4. Right? And this is really an x to the 0, the next term. So this is going to be 4x. Again, if you think you might have done, a mental block, just take each term and take the derivative. Okay, so the 3 stays out front, 2x cancels the 2, I get 3x. Take the derivative here, I just get the 4. Okay, so when you move on to calculus, right, and in engineering this is important too, so we can follow what you're doing. But really, in the math department, you got to be anal about your notation, right? So make sure you write these steps out, exactly the way they need to be. Integral sign, then you get the answer, then you put the limits that you're going to evaluate. Okay, typically over on the right-hand side like this. Okay, and then what that means is I evaluate the whole expression at the top limit, and then I subtract the whole expression at the bottom limit. So W is 2 times, it's going to be 1 cubed divided by 3. Okay, I understand this is more writing than you would probably need, but I'm just trying to be clear. 3 times 1 squared divided by 2, all right, plus 4 times 1. And then keep in mind, I still have the bottom limit, even though with this polynomial, I'm tempted to just say, like, I'm done right now. All right, because when I do the bottom limit, I have to subtract the rest of this, right? And what I'm really doing is 2 times 0 cubed over 3 plus 3 times 0 squared over 2 plus 4 times 0. Okay, and so the thing is, when you move forward, okay, even in this class, you're going to be tempted not to write all this out. Okay, and in cases where it's obvious, like a polynomial, I'm good with that. Okay, but if you get in this habit of every time my limit has a 0, I'm going to not worry about it, it's a dangerous road. Okay, and the next two functions are going to show why that is. Okay, so not a bad idea to just be anal and put it all in there, knowing that all of this is just 0, right? Every term is 0. So finally then, for this first function, you know, I can work on my fractions here if I want, right? But I've got 2/3. It's 2/3 plus it's 3/2, okay, plus it's 4. So I can get a common denominator on this, which looks like it'll be 6, and I can get an exact number, or somebody can give me a decimal. What do we got for this? Say again? 6.167. 6.17 to 3 digits, Newton meters. Okay, yeah, if you get a common denominator of a 6, I think the exact number, 37 over 6 is what that works out to be. Questions? All right, let's look at another one of these. Okay, how about B? 2 times the sine pi over 2x plus 3 times the cosine pi over 2x. Okay, and so part B, W is equal to the integral 0 to d, 0 to 1, and it's going to be 2 times the sine pi over 2x plus 3 times the cosine of pi over 2x dx. So same story, now I've got 2 terms instead of 1. I got to do them one at a time. Okay, and then I got to evaluate the limits. So help me out. First term, what do I do with the 2 in front? It's a constant, it stays there. So I need now to integrate the sine of pi over 2x. Again, if you never had integrals before, right, you got the formula right here. Right? So it's a sine omega x where the omega is what? Pi over 2. All right? And so according to the sheet, when I integrate the sine, I get a negative cosine, but I have to divide by the omega. Right? And so, help me out. Who wants to try this? Okay, so dividing by it is multiplying by the reciprocal. So negative 2 over pi, right, times, I have the cosine, pi over 2x, like that. Okay, now with this negative here, okay, you probably want to put another parentheses to be clear. This 2 stayed out front. This is multiplied. When I integrate this guy, I get minus 2 over pi times the cosine. How do I know I did it right? I could take the derivative. If I take the derivative, minus 2 over pi stays. Derivative of cosine is minus the sine, so the minus is gone. The pi over 2 comes out, cancels the 2 over pi, and I'm back to just the sine. You guys with me? All right, again, if you can do this, in one math without the in-between parentheses, that's fine. Okay, our general rule of thumb for showing your work is if it's conceivable that you could do from step 1 to step 2 in your head, we always give you the benefit of the doubt. The problem is if it's wrong, like the worse that it is butchered, right, in the wrongness, if we don't see a place where the mistake was, it's harder to give the partial credit. Okay, so you just got to get comfortable at what level you feel like doing. But if it can be done, you know, in your head from step 1 to step 2, you won't be penalized for it, as long as it's correct. Okay? And then here, next term, what do I do with the 3? Out front. Then I got to integrate now the cosine. I integrated the sine here. Integral of the cosine is what? Yeah, it's now a positive sign, right? Okay, and what do I do with this pi over 2, the omega? Out front. So I got to flip it upside down, 2 over pi, and I get the sine pi over 2x, right? Like that. Okay, and then finally, bracket on the outside, limits 0 to 1. All right, so I can simplify this stuff a little bit here, right? Because I've got the 2 here and this, and the 3 here and that. I could pull the 2 over pi out front of this entire thing if I want. Okay, or I could leave it in there. I would tend probably to pull it out front. Okay, and so if I put 2 over pi out front, right, then I will have to evaluate now what? Negative 2 cosine pi over 2x, right, plus 3 times the sine pi over 2x, right, and I've got to evaluate that at the 2 limits. So this is a good example of why you got to be careful, okay, when you do these limits top and bottom when you have a trig function. So let's do them, see what happens. 2 over pi out front. Okay, first term, I got to evaluate this whole thing at the top limit. So it's minus 2 times the cosine of pi over 2, right, times 1. That's the top limit. Plus I got 3 times the sine of pi over 2 times 1. Okay, so this is the top limit right here. Then I have to do the bottom limit. Okay, and so I'll say minus everything in the brackets here. Okay, and I got to evaluate now at 0. So I'll have minus 2 times the cosine pi over 2 times 0. Right, and then I'll have plus 3 times the sine pi over 2 times 0. Okay, and so the thing is, when I evaluate trig functions at x equals 0, do I necessarily get 0? No, right? It depends which function it is. So you can't just ignore a bottom limit just because it's 0. Incidentally, a note on the evaluation here. Okay, this is the answer for the whole thing with the 2 limits. One way to look at it is do the entire thing at the top limit and subtract the entire thing at the bottom limit. But I could also look at each one of these terms as its own separate integral. So I could put the limits around the first term and then the limits around the second term. I don't care how you do it. Okay? So you could do it term by term, right? Where I have the cosine top limit minus the cosine bottom limit here, sine top limit, sine bottom limit here, right? Or I could write it out like this. Okay? So if you think about it one or the other way, whatever you're more comfortable, it's fine. All right, so let's bang this out. So W equals, I got the 2 over pi out front. And the first term, what's the cosine of pi over 2? Yeah, so I get 0 for the first term, right? And then I got plus 3 times the sine of pi over 2. What's that? Yeah, sine of pi over 2 is 1. So this is the first term. It's 2 over pi times 0 plus 3. Second term, right, is 2 over pi. This needs a 2 over pi. Who didn't catch this? All of you guys? Right? 2 over pi is times the entire thing, right? So top limit, bottom limit. Okay, and so the next one I'm going to have a negative minus 2 over pi. And then I've got top limit times the bottom limit. Top limit minus the bottom limit. So what's the cosine of 0? 1. So this is going to be negative 2 right here. Right. Okay, and then what about the sine of 0? 0. Okay, so what do we have here? W apparently is 2 over pi times 3, which is 6 over pi, minus 2 over pi times negative 2. Minus a negative is a plus 4 over pi. Boy, that's weird looking algebra. What's 6 over pi plus 4 over pi? 10 over pi. This is 10 divided by pi. So that's the exact number, or you could get a decimal for that. Yeah, I got 3.18 Newton meters. Okay. All right, so again, the first one, you can still see the answer left over. Polynomial, I got 6.17 Newton meters. Over here with the sine and cosine, I got 3.18 Newton meters. Different force gets me to the same location. Okay, takes less energy to do it with this particular force. Questions on that? Okay, so let's look at the last one. E to the pi x. Okay, the exponentials, they can pop up in mechanics problems. You see them a lot in circuits problems. Things like capacitors, discharging, right? I can get exponential type answers for that. Okay, so part C, the work now, integral from 0 to d, 0 to 1 of f of x dx. So it's going to be 4 e to the pi x dx. A little less writing than the last one. So what do I do with the 4? Keep it out front. So I got 4, and then e to the pi x. What is the integral of e to the pi x? I get e to the pi x again, right? The exponential function is the function that when I take its derivative or I take its integral, I get the same function, except it's scaled by a number. Yeah, I got to put a 1 over pi, right? So this is e to the sx. The integral is 1 over s times e to the sx. So I will get 1 over pi e to the pi x. How do I know if that's correct? Take the derivative. Okay, if I take the derivative of this, I will get the pi out front, cancel the pi, 4 stays, back up to this. You guys with me? Yes. Okay, so then I have to put the limits, 0 to 1. So again, I can pull the constant out front, right? When I do the limits, this constant is with each term. So you can write this as 4 over pi, right, times e to the pi times 1 minus e to the pi times 0, right? Top and bottom limits. Is e to the 0 equal to 0? No, right? It's equal to 1. So again, bottom limit is 0. Doesn't mean you can just do the top limit. Okay, and so if you look at this, w is equal to 4 over pi, and what I'm going to get is e to the pi minus 1 right there. Okay, and of course I can get a decimal for that. Who wants to take a crack at it? I didn't get that.
In terms of pi?
Now give me an actual decimal. 28.19, that looks right. 28.2 is what I've got here, Newton meters. Okay, so clearly if I'm going to move this block and I'm controlling the force along the distance to get it there, okay, looks like the exponential here takes the most amount of work, 28.2. And then I've got over here 6.17 for the polynomial, and what we had for the sine and cosine was only 3.18. Okay, so different functions, different amount of work. Note that none of these talks about how long it took to get there or, those kind of things, the acceleration, right? It is just an energy consideration. Questions? All right, so moving forward, integrals in statics. Okay, and one thing I like to always kind of give an overview before we do the integrals in statics. Okay, when we conceived the materials for this course, this point right here, integrals in statics, the way we actually use integrals in statics, centroids and centers of mass, distributed loads, resultants of forces and moments, those kind of things. It's why we need integrals for statics. This is the peak of kind of the conceptual demands of this class. Okay? So everything we do after I get through this set of notes is easier than what we're going to do now. Okay, so I just like you to have that big picture. So it's also a sense that, if we go through all this and you're kind of getting what I'm saying, but it's not that easy for you to grasp and you got to go home and think about it more, that's normal. That's what we expect. Okay? If I get through the next lecture and a half and you're like, piece of cake, then you're in good shape, right? Because moving forward, when we start doubling back and doing integrals and dynamics and integrals and circuits, it really brings it all together, right? Once we've done those derivatives, what we do with the integrals, in some sense, almost just makes all the problems you've already done easier, right? And it's easier to cover. Okay, so we are still pushing kind of the new learning with this material, which is integrals in statics. Okay, so concept for today. Also, on the homework that's assigned, okay, is centroids, centers of mass. Okay, so this is integrals in statics. Okay, and if you remember, statics is about adding up the forces to get 0. Right? And so, for example, ME 2120, there's a BME version of this class as well. Okay, and again, one of the biggest reasons we need this is to talk about centers of gravity, okay, which is also referred to as centroids. Okay, centers of gravity also, by the way, centers of mass is the other term for that. So just for my own entertainment, okay, when I took calculus in high school, we went through it was like a year and a half we went through a whole calculus book. This topic is in calculus books, okay? Centroids, centers of mass. Raise your hand if you've done centroids and centers of mass using calculus before. Okay, so one thing I want to point out to most of the population here, every time I ask this question throughout the course, less hands go up. All right, so we're down to like 3 people in the entire room of 91 that have seen this. Okay, so just you understanding where we're going here. Okay, and so it's in kind of an advanced application. In the calculus book, it's, if we get to this section, it's section like 8.9 with a star on the end. Okay, the reality is, this is the most important thing, okay, that we need over here in engineering, right? So we're trying to front end all of that and say, look, as opposed to this being some application maybe we get to if we feel like we've learned it enough, no, this is the whole point. This is why you need integrals, okay? This, and then how we apply this to problems with distributed loads. Okay, and the nice thing about this is for engineers, I mean, this is a pretty straightforward idea, center of gravity. So, what do I mean exactly by a center of gravity? Let's say that I take any piece of material, okay, and it can have any kind of shape, like this. Okay, and so let's say this shape, I'm going to write it down as a function. Y is a function of x, okay, and to simplify this notation, here's my triple equals again, means like by definition, I'm just going to call this y of x. Right, so y is the function of x. Okay, and whatever this is, okay, I'd like to be able to identify where is the center of mass. Okay, and so anybody want to suggest to me why do I care where the center of mass is?
It's where a lot of your load's going to be at.
It's where your load is going to be.
Like say, you're trying to figure out for like a lever or an arm, like a robot arm.
Okay.
And that's where it's going to snap probably first.
It's going to snap at the center of mass? I don't know if that's true or not.
That's going to be your strongest point.
The strongest point. Other thoughts?
That's where it's all balanced.
That's where it's balanced. What do you mean by that?
In any direction, it has an equal load.
In any direction it has an equal load. So you talked about a lever and a robot also, right? So it's like this, right? If I want to balance, hard with something that rolls, but if I want to balance the marker on my finger, right, then probably I got to put the marker at the center of mass, which, where is that? The most obvious statement would be, well, duh, it's in the middle. But again, if it's not uniform, right, like this marker isn't exactly uniform. It's got a cap on one end, right, and the rest of it's a cylinder. So this is not like exactly halfway down the length, right? It's somewhere else. Okay, now this problem's a little more complicated. This is a 3-dimensional volume. Okay, it's axisymmetric, so you could do this in 2D. Okay, but the point is, real objects with different shapes, they've got material distributed throughout. It might not even be the same material. So even if the shape looks uniform, might have more density in one region than the other, right? And so comments like, well, it's where the force is, or it's where it balances, you're on the right track. Okay, let me ask you this. If the forces don't add up to 0, what do they add up to? They add up to forces. That's true. That's true, yeah. Well, what I'm saying is if I have an object with forces on it and they don't add up to 0, the vectors don't add up to 0, then the question is, what do they add up to? Acceleration, is that it? Does the units work out? Does force equal acceleration? You're getting warm. Mass times acceleration. Okay, again, if you haven't had physics, this is okay, but I've made this point before. Things are balanced, forces give you 0. Things are not balanced, stuff starts going, okay? F equals ma, Newton's second law. Okay, if I have a 3-dimensional object, a 2-dimensional object with forces on it, F equals ma, what's the A? Is it the A of this point over here? Is it the A of that point over there? Say what? It's the A of the center of gravity, right? And it is the result, right, of applying F equals ma in a distributed way throughout the entire thing. And you got to find a place where you're basically at the middle, right? So it's the statement of what does the middle mean when I don't have something obvious like a circle? Well, the middle is the middle, right? A square, the middle is the middle. This thing, I don't know where the middle is. You know, what's the middle? Is it halfway up the y? Is it halfway out to the x? Yeah, so what you want to think about in these things is, A, I need to know where it is because the mechanics, whether or not it can balance, when I do the mechanics, sum of the forces equals mass times acceleration, right? The dynamics, whether or not it's rotating, all of these things are about the center of mass. Finding the center of mass is the first step to doing rigid body analysis of any type. Okay, so it's important stuff. So, here's the beauty of it. Very intuitive. Right? To figure out where a center of mass would be, you know, what you want to basically say to yourself is, what if I could take this thing, right? And again, the idea is this, it's this whole shaded region right here, right, is what I'm talking about, a piece of material. If I could pull this thing off the board, tip it like this, and balance it on my finger, where would my finger have to be? Right? And so you can look at it and say, well, you know, my finger is probably not going to be way over here. Right? The origin's not going to work. Right? And so you can kind of come in here and just look at where do I think the fat spot is. Right? And then you apply the Klingbeil theorem. Okay? And you can get pretty accurate with this guess. Okay? You see right there. That's the middle. Okay, but what we'd really like to know to do our analysis is you got to come in here and say, well, I actually need coordinates of this point. So this is G, right? The center of gravity, right? And I'm going to write it as coordinates. It's going to have coordinates x. I'm going to call it x bar, and coordinate y, y bar. Okay, and literally what I mean by that is x bar is this distance right here, right? How far is it from the y-axis? And y bar is this distance right here. How far is it from the x-axis? Okay, so what I want to know is exactly what are the coordinates of x bar and y bar. If I know that, then I can start adding up some forces, right? And, you know, applying them to the center of gravity and all those things, right? Taking moments, all of that mechanics. Okay, so the point is G, x bar, y bar, that is the center of gravity. Okay, and if this thing is uniform material, okay, then you could say that it is center of mass, okay, which is where we'll use it in mechanics. All right, so why do you think I use the bar, x bar and y bar? Where else have we used a bar in here? What other context did we use a bar over a letter? Say what? Velocity. What was the other one? Vectors? Use it vectors? That was hats. We used hats on vectors. We used vertical bars on the side, magnitude of vectors. Horizontal bar, we used it in velocity to denote what? Average. Right? The reason we use x bar and y bar right here as the coordinates of the centroid is, in a fundamental way, that's what we mean the middle is. Right? It is the average location of all the material. On average, right, this is the average location. Right? So sort of equally distributed about that point, which is, I think, the comment made here. Right? So that's it. It's the average value. So it begs the question, like, how do you calculate an average? Right? If x bar is the average location of material, right? And I'll call it area, just to be clear. Average location of the area. Okay, how would I calculate that? How do you calculate an average of anything? Average on exam number 1. Add them up, divide by the total. So, add it up, divide by the total. So what do you think you'll be adding up if you're trying to figure out, okay, I'll try and ask this in a leading way. If all the pieces of this area, okay, are equally distributed about a certain point, then what do you think I'm adding up? The pieces of the area, right? And then to average it, I'm probably dividing by what? How many pieces you have? Close. Close. Each one of those pieces is a piece of area, right? What was that? I think I heard it. Somebody said total area, right? So what I want to do is think about, like, on average, any given piece is a certain distance away, has an x coordinate. Some other piece has another x coordinate. I want to do like a weighted average here, right? Take the piece, multiply by how far away it is, add them all up, but then divide out the total area, right? And I'm back down to a unit on x. So the way we can write that is, back to this summation guy again, I can add up every little piece of area multiplied by its own location. So I'll take x bar I of any ith piece, right? So I got I equals 1 to however many pieces of area. I'll take x bar of that piece, multiply it by its own area, one little piece, okay? And then I will divide it by the total area. Okay, so I could do this with any kind of pieces I want, right? I mean, so I could think about one piece right here, okay? And this one piece right here might have an area AI, right? And it might have coordinates on it, right here. The coordinates of this piece right here might be x bar I, y bar I, okay? I can use any shape or size piece I want to do this calculation at any location in here. If I know where this piece is located, then I can just take, hey, its area AI times its location, and I'll have a measure of how far that piece is. And then I will add up every one of these measures, divide by the total area. That's what I get when I add up all the pieces, right? And look what happens to the units. The area cancels out, and all you're left with is an x value. Okay, so it is a weighted average. It's a weighted average of all the pieces of the material. Okay, so if that is what we do for x, then if I want to do y, average location, the y bar of the area, then I can do a similar argument. Y bar would be the summation. I'll take all of the y locations of every piece of area, y bar I times ai. I'll add up every single one of those, however many I use, and I will divide that by the total area, ai. And so far, this is kind of just like a conceptual formula for this, right? I could have any kind of area. I haven't even said what the function is. I could use any kind of little piece of area in order to do this, right? And I'm just making the statement that here's my plan. If I can't tell exactly where the middle is, right? Like if this was a square, I'd be done, right? I'd say the middle is in the middle. I'm done. Okay, but because this isn't a square, I'm not sure where it is. So I say it's about here. I'm going to have to average this thing out by breaking it into pieces. Okay. So the question is, how can we do this in a systematic way with pieces that it's easy to calculate where they are, right? And come up with a formula that would work for any area bounded by any function, y equals f of x. Okay, if I have that, then I can calculate the center of whatever I want. Okay? And that's the goal of this topic. Questions about the plan before we move forward? Okay, so let's think about this. Take the same shape and let's break this thing into pieces that might be easy for us to deal with. Okay, so let me take, again, very similar shape to that. Okay, so here it is again. Okay, and so I'll have, this is the y-axis. This is the x-axis. I'd like to calculate the total centroid of this thing. Okay, so this is the area I'm talking about, bounded here. Okay. Here's what I would propose. If I put any function right here, right, this is y function of x, which I'm going to denote as y of x. Okay? Every value of x gives me a y value. The piece I would like to use for this is a rectangle. Okay, so I'm going to come over here and I'm going to draw me a rectangle to represent my piece of area. Okay? Again, it is up to me what I use to represent a piece of area. Who wants to suggest for me why would I want to use a rectangle? Easy to calculate its area. Okay, so let's do that first. So clearly, you know where I'm going with this. I want to get this accurate, so I'm going to use an infinite number of these rectangles. Okay? And so if that's true, then I know the width of the rectangle is probably going to be what? Yeah, this is infinitely thin. I'm going to call it dx. Okay? Then you said it's easy to calculate the area. Okay? And I would argue that's true, right? So how do you calculate the area of a rectangle? Yeah, it's the width times the height. So here's the thing. Hey, if this guy is located any value of x, okay, x could be 0, x could be all the way over here at the end, okay, whatever that is. Okay, for any value of x, how would I get the height of this rectangle? Yeah, I got to evaluate the function because I drew the rectangle so that it was inscribed inside the area. So the coordinate of this point right here is x, y, right? But keep in mind, y is a function of x, right? So I will just evaluate the function at whatever x value I drew this rectangle. That's the height. So if that's true, then I can write down the area of this thing. The cross-hatched area right here, I'm going to write it as dA because it's infinitely thin. It's an infinitesimal area. Okay? And so, apparently it's the width times the height. I'm going to write this as y of x dx. Great. So here's the thing. I want to evaluate these two formulas for this picture. So right away, the dA represents what in these formulas? It's the AI, right? This is the ith rectangle. I'm going to have infinity for the total number. This is the ith one. Okay, so this is right here. This is the AI. So I already got an AI. So now the question is, what are these? What's the x bar I and the y bar I? According to this, that's the middle of whatever piece I've used here. So where's the middle of this piece? This rectangle. So it's a rectangle, right? One reason I chose it is because I can eyeball the middle and get it right, right? The middle is halfway up, yes? So here's the middle right there. And that middle has coordinates, right? The coordinates of the middle here are the x bar I and the y bar I, right? Of the ith area over here. And we can write down what those are. What's the x coordinate of that rectangle? X, right? You didn't even have to ask me about, I didn't have to ask you about grants too, right? Okay, so there's X. Where's the Y coordinate? Right here. So to get the middle of this rectangle, is that the Y value? It's half the Y value, right? So this Y bar I apparently is the function y of x divided by 2. So apparently I've got everything I need to evaluate this formula, right? I got an x bar I got an ai, I got a y bar I got to do a summation. Of course, what I'm adding up, how many of them are there? An infinite number, so this summation sign is really better be what? An integral sign, right? Adding up an infinite number of these. Okay, and so here's the statement. When I now draw the picture and identify what's going to be my little piece of area so I can do a weighted average here, okay, then this formula that looks like algebra, okay, turns into a formula that looks more like calculus. So x bar summation x bar I ai divided by the summation of ai, this becomes x bar I is whatever x value I'm talking about. The summation up here becomes an integral sign. So I've got x, and the ai over here is the dA, right? So I'll write that dA, and I'm going to divide by the sum of all the dAs. Okay, but if I know y equals a function of x, the dA is actually this. It's the function y of x times dx. So now this becomes the integral, right, of x times y of x dx. All right, and in the denominator, I get the integral of y of x dx. By the way, when I integrate y of x dx, what does that give me? If I take any function and I do the integral of the function, it gives me what? It gives me the area, right? It gives me the total crosshatched area A. So keep in mind, this denominator is just the area, right? If I know the total area, it's just A. That's what the denominator is, okay? Now, y bar, I need the summation y bar I, ai, divided by the sum of the ai's. And let's see what we get there. All right, this is the integral. What's the y bar? Y bar I is what, according to my picture here? Yeah, it's y of x over 2. So I'm going to write that as 1/2 y of x. All right, that's y of x over 2. Then I have ai, so I'll still write that as dA. All right, divided by, down here, the integral of dA. Okay, and so when I plug in over here for dA, dA is y of x dx. So I'm going to have 1/2 y of x times y of x again, right? dx. So this will be the integral 1/2 y of x multiplied by itself squared dx divided by the total area, the integral of y of x dx. right? So recognizing that the bottom is the area, the simpler way to write this is x bar is, if the bottom's the area, it's 1 over the area times the integral of x, y of x dx, right? And y bar is 1 over the area, right? And now I'm going to integrate 1/2 y of x squared dx, okay? Where A is the total area of the cross-hatched region. Okay, so these guys right here, okay, will give you the answer for vertical rectangles, right? Anytime I take a function and the area is the area bounded by the function, right, and the coordinate axes, right, namely the x-axis, right, then those are formulas that will work. Okay, now keep in mind, when I do this, I'm calculating areas, I'm going to get a number, right, not a function. So to be clear about this, you really probably have to put a limit here, right? We'll call B the width of this thing. So these guys really 0 to B, where B is the width of that region, right, from here to here. Okay, and so these now are like formulas, right? They're calculus formulas, okay, for, you know, these are good for vertical rectangles. Okay, and the beauty of this is I could come in here and I could say, I'm going to break this thing up into whatever I want. Maybe I'm going to use little squares and I'll call it dx and dy, right? Or maybe I'll use horizontal rectangles and I'll call it dy. It's up to me. Okay, what I just did is I said, hey, I'm going to use right now a vertical rectangle. And if I use that, this is what the formula looks like. Okay, so we want you to understand how to set up an integral, right? And if you end up with something that's hard to calculate by hand, that's why we got MATLAB, okay? That's why we got TI-89s. But the ability to understand how to come up with this and why this matters, this is the key thing we want you to be able to leave this class with. All right, so at this point, let me recap what I said. If you're sitting back looking at this going, man, we were doing algebraic equations a couple weeks ago. Now I got integral signs all over the board and summations, and it's going to take me a while to digest this. That's normal, okay? You're supposed to feel like that. Okay? And so you'll have time to go home and work on the problems and such. But this should become more concrete to you as we actually start to calculate some centroids of some actual regions. Okay, so I'd like to move away from this general argument here and see if, you know, can we look at something that actually has a physical shape we can understand here and calculate where the middle is. Any questions before I move forward? All right, so here's a good one. What if I have, for example, a triangular region? Okay, so what you're going to get when you're done here is a geometric answer. This is going to be the centroid of a triangle. Okay, and so how can we calculate the centroid of a triangle? Okay, by representing a triangle as though it's a function. Okay, so here's how we're going to do it. This is the y-axis. This is the x-axis. I want to figure out what the centroid is of a triangle. Okay, right here. And so I need to be clear about how big the triangle is. So we'll use the same definitions from like geometry class, right? So this is h for the height, and then the base, we'll just use b, like that. Okay. So what I would like to be able to do is apply this idea of these vertical rectangles, right? These averaging of the areas to this shape, right? And see what I get. So nice thing again about centroids is that it's pretty intuitive to look at this and have a sense where it is. All right, like so for example, do you think the centroid's over here? No. Right? If I pull this thing off the board and try and balance it on my finger, can I hold it right here? No. What about all the way at the origin? Is it, do you think, halfway up the y-axis? You know, so here? Halfway in the x? No, right? So probably a little more towards the origin. Not halfway. I don't know the answer. Probably have to do some calculus here. All right, so, well, come in here. Klingbeil theorem. Find the middle. It's right there. Okay, that's where it is. And what I like to do is figure out, what is that location? This is x bar, y bar, g. Okay. So I could take this thing from scratch, right? And I could draw a rectangle and I could identify all these things, but I just did that for any shape, right? This is the answer. Okay, so let's just go ahead and take this answer and see if we can't evaluate some integrals here. All right, so x bar apparently is going to be, I need the total area, 1 over a, but I need the integral of x times y of x dx. And I can see I'm going to have limits on here, right? Yeah, b is the x direction, right? So this will be 0 to b. And I'm going to need y bar, same thing, 1 over a. We'll have an integral. I got a formula over there. All right, it looks like 1/2 times y of x quantity squared dx. Now, if I'm calculating the y bar value, what should the limit be now? Should it be 0 to h? Let me ask you this. Where's the first rectangle located? This is the ith rectangle. Where's the first one? Right here, right? And every one of these rectangles, I'm going to calculate the middle of this rectangle, the x and the y. The first one's here, the next one's here, and the rectangles keep going, right? And I add them all up. Whether I'm calculating the x bar or the y bar, I'm going this way, right? Okay, so look, the limit quick check is determined by this guy. If this is a dx, it's what's the range of x values, but what you're doing is you're stacking them in the x direction, right, as you add them up. So it's still 0 to b because I'm using these horizontal rectangles, or sorry, vertical rectangles. Okay, all right, great. So apparently, if I'm going to evaluate this, what I need is I need an equation for y of x. Okay, so I don't know. How am I going to find this guy? Y of x equals what? What kind of function is it that represents the hypotenuse of a triangle? It's linear. Do we know the equation of a line? It's the reason why we cover that, right at the beginning of the course. Important stuff. So in general, the equation of a line is what? Y equals mx plus b. Now you need to be a little careful because I got a b on the board already here. All right, so y equals mx plus b. What's the m? Okay, so for this problem, what's the m? What's the slope of this line? It's minus h over b, right? Down h over b. Yes? Okay, so y of x is minus h over b, that's the slope, times x, plus I need the y-intercept, right? Y-intercept is what? H. Okay, great. So we got an equation. All right, y of x is minus h over bx plus h. All right, so at this point, this is it. You're just cranking out the integral. Oh, by the way, do I need to do an integral to calculate the area A? What's this area? Yeah, it's 1/2, right? The base times the height. How do you think you calculate that area? A couple ways. One is to do the rectangle and realize this is half of it. Okay, it's the obvious way. Okay, the other way is to evaluate the integral y of x dx, and if you do that exercise, this is what you'll get. Okay, so that is the area, but if I know that, I don't have to spend time on it. So we'll say x bar is 1 over a, right? So it's bh over 2. 1 over that is 2, right, over b times h, right? That's 1 over a times the integral from 0 to b of x times y of x dx minus h over b, right, times x plus h dx. So, got to work this integral. So I got a 2 over bh out front, 2 over b times h. I got an integral with limits 0 to b. Easiest way to do this, probably just distribute this through. All right, so it's going to be minus h over b times x squared, plus I got h times x dx. Questions on that? Because at this point, we're just cranking out an antiderivative, right? That's it, applying this formula. You guys with me? Say that again. Is it 2b? So we're calculating this guy, 1 over a times x y of x. A is bh divided by 2. So 1 over a is 2 over bh. Okay, and then right here, I just distributed the x. I have not done the integral yet. Okay, you guys with me? So haven't done the integral, just distributed the algebra. Okay, good. So 2 over bh, now I'm doing the integral. Look, the way you'll know is I'll have a square bracket when I'm done, right? So integral sign, I'm still inside. All right, so let's crank through this. So the integral h over bx squared, what do I do with the h over b? I leave it. H and b are just parameters, right? They're not functions of x, they're constants. Minus h over b, I got to integrate x squared. What do I get?
2x.
Not 2x, that's the derivative. Backwards. X cubed divided by 3, okay? So h over b out front, x cubed over 3. Plus the next term, I got h. Integral of x is what? X squared divided by 2. I got limits, 0 to b. So x bar, it's going to be 2 over b times h. Okay, and this is where you got to be on top of your algebra here. So we'll write it out. Minus h over b, top limit, I'm going to put a b where I see an x, right? So it's b cubed divided by 3 plus h, put a b where I see an x, b squared divided by 2, and let me evaluate the bottom limit. What do I get when I do the bottom limit? 0, 0. I'm going to write this as 0 plus 0, just to make it clear that I've done the bottom limit, okay, and I've gotten 0 for each of the terms. So x bar, I got 2 over bh out front. Okay, and so what do I have here? This is minus h over b times b cubed over 3. Isn't that minus hb squared divided by 3? One of the b's cancels. And then over here I got plus hb squared over 2. Can I simplify that? What's hb squared over 2 minus hb squared over 3? Let me ask it another way. What's 1/2 minus 1/3? These are like terms, right? hb squared, it could be x, it could be y, it's just a term. So 1/2 minus 1/3 is what? It's 1/6, right? It's 3/6 minus 2/6 is 1/6. So it's 1/6, right? So don't I just get hb squared divided by 6? Can I simplify that? What happens to the h? H cancels, one of the b's cancels. What happens with the 2 and the 6? Becomes 1/3, right? The answer is b divided by 3. Does that make sense? It's not halfway. It's not all the way at the edge. It's 1/3 of the way. Let's do the y direction, and then we'll get out of here for today. By the way, what has to be the answer in the y direction? It's got to be h over 3, right? Nothing stopping me from taking the same physical problem, pulling it off the board, rotating it, and calling this h. The physical location doesn't move, right? The answer has to be h over 3. It's a symmetry argument. Okay, But the math, if I were you, I'd want to see some proof that this works, okay? If I saw that the first time, so let's crank it out. So it's 1 over a, that's still 2 over bh, and it's the integral still 0 to b. According to the formula, I got 1/2 y of x squared. 1/2, I got to put the whole function in there, minus h over b x plus h squared dx. Okay, so that is the y bar, right? 1 over a times 1/2 y of x squared. So, again, if you've had different techniques of integration, there's ways to do some simplification. If you've had some calculus, you can do things, change some limits around. We're not getting into all that in here. Okay, you will do problems that can be done by brute force and the formula sheet. Okay, so this one, I can expand this out, right? So 2 over bh right here, integral 0 to b. By the way, what can I do with this 1/2? I could pull it out. Let's do that. 1 over bh, that simplifies things. Now I got to expand this. It'll be the first term squared, h squared over b squared x squared, minus 2 times the first times the second, 2h over b xh, plus the last one, h squared dx. Okay, that is just algebra for how to expand a binomial squared. All right, first term squared, 2 times these two, last term squared. So one at a time, I can do the integral. I got 1 over bh, and now here, what do I do with the h squared over b squared? I leave it. Integral of x squared gives me x cubed over 3. Next term, I got minus 2, right? H over b. I got another h here, h squared. Yeah, x squared divided by 2 for the integral of x. Okay, and then how about the last term? I got h squared times what? X, right? That's an x to the 0 term. Again, when in doubt, take the derivative. I get h squared, okay? And then I evaluate between 0 and b. All right, so let's plug in the limits. 1 over bh, what do we get? If I plug in a b right here and another b right there, what will I have? H squared over b squared, b cubed over 3, h squared, right? B cubed, b squared gives me b, divided by 3, minus the 2 cancels, h squared here, b squared cancels a b. Is this not just h squared b? Plus, this is interesting, h squared, plug in the top limit, b. Then I have the bottom limit, minus 0 plus 0 plus 0. It's a polynomial. You guys with me on the algebra? Let me recap. B cubed cancels b squared, gives me a b. H squared and 3 still there. 2 cancels, h squared still there. B here, b squared cancels a b, I have 1b. This one, h squared, and I have a b. So this simplifies itself in a hurry because minus h squared b plus h squared b is what? 0. So I get 1 over bh times h squared b over 3. What happens to the b? B is gone. One of the h's is gone. Y bar, h over 3. Okay? Why do calculus profs complain about student performance in calculus? What do they always say? They can't do algebra. This is what they're talking about, right? To work calculus problems, there's algebra all over the place. So good practice for this. All right, more on this next time, guys. Going to finish this up and do more statics.